Okay, today you are going to be listening to a mini lesson on one of the principles of passive transport called diffusion and osmosis. Before we begin talking about diffusion and osmosis, I should probably explain what passive transport is, because you have not yet watched that portion of our mini lessons, but it is the next thing that you will be watching. So passive transport is the movement of molecules across a membrane without the use of energy. And the energy of cells is ATP, so it's without the use of ATP. This is particularly important to understand because it helps us understand how cells get molecules in and out of themselves. So diffusion is one example of passive transport. And diffusion is simply molecules which tend to move from an area of high concentration to an area of low concentration. You can think of the analogy of a rock rolling down a hill. Remember, passive transport is the movement of molecules that does not require energy. And rolling a rock down a hill from a high area to a low area also doesn't require energy. So imagine a rock rolling down a hill from high to low. That doesn't require energy. That's diffusion. The only difference is that diffusion deals with the movement of molecules. So if you look at this demonstration in the upper right-hand corner, you see the small purple dots, which are meant to represent molecules, moving from an area of high concentration in the lower left-hand corner out to an area of low concentration. So why does it happen? It's important to understand why things move from high concentration to low concentration. Most of you probably understand why molecules move, or why a rock might move from a high place to a low place. That's gravity. So why do molecules do the same thing, move from high to low concentration? And there are three principles that control this. The first that you need to understand is that all molecules are in constant motion. Okay? All molecules are moving at all times. When molecules are close together, they're going to be bouncing off each other. And this makes sense. As you're closer together, you're more likely to run into another molecule and then be pushed away from each other. The farther apart you are, the less likely you are to run into each other. So again, as we see in this demonstration, these molecules are more likely to run into each other when they're in this upper right-hand corner, causing them to, over time, spread out and take up most of the space. And the last principle, which I've already addressed in our concept of what a passive transport is that no energy is required for this to happen because all molecules are in constant motion. That's just a fact. And when molecules are close together, they tend to bounce off each other. So I have a simulation that I'd like you to watch here. And I'm going to move this up into our view so we can see it. And here we see small red and blue molecules which are bouncing around. And I can restart it in a corner, creating an area of high concentration. And those small red and blue molecules are going to move from an area of high concentration to an area of low concentration. And it doesn't matter where I start it. They can start in the middle. They can start at the edge. But they will always move from that area of high concentration to an area of low concentration because they are more likely to run into each other when they're close together and less likely to run into each other when they're far away. And again, no energy is required for this to happen. So when does diffusion stop? When all molecules are equally concentrated in all areas, they're said to be at equilibrium. When that happens, molecules are no longer going through diffusion, and diffusion has stopped. However, it's important to understand that molecules do continue to move even during that time. So again, if we look at our diffusion simulation and we begin the molecules in a concentrated state, diffusion is still occurring. And at this point, if you look at the simulation, the blue and the red molecules are found equally everywhere in the screen, which means that diffusion has stopped. They have reached equilibrium. However, they have not themselves stopped moving. So if we again, diffusion is still occurring, and now equilibrium has been reached. Okay? So diffusion is still occurring, and now equilibrium has been reached. Okay. So what's osmosis then? Osmosis is simply a special kind of diffusion. Okay? It's diffusion that involves water. Okay? Osmosis is always about the water. Every time you hear the word osmosis, the first thing that should come to your mind is water. You're interested in where the concentration of water is. So in this example here, where water represents the small blue spheres, we see that the high concentration of water is on the left side, the low concentration is on the right side. So the arrow shows that water will tend to move from the left to the right across a membrane. Here is our membrane right here. This represents a membrane. And like all molecules, they tend to move from high to low concentration. It's just that water movement is so important to living things that we give the diffusion of water a special name, and we call it osmosis. And I should add one thing to our definition here. Diffusion involving water across a membrane. And this is why it's so important to living things, because we're interested in how water moves across a membrane. So if we imagine a cell floating in a solution, it's worthwhile to understand the relationship between the water concentration inside of the cell and the water concentration outside of the cell. Inside of the cell, there will be a certain concentration of water. Outside of the cell, there will be a certain concentration of water. When the higher concentration of water is inside of the cell, we call that solution hypertonic. Okay? More water in the cell. Hyper means more. Okay? And in this case, because molecules move from high to low, water is going to move from high concentration, 80% inside, to a low concentration, 77% outside. The water will move out of the cell. H2O will move out, which will cause the cell to shrink in size. A hypotonic solution. In this case, the higher concentration of water is outside the cell rather than inside the cell. 80% outside, 70% inside. Water will move from the outside in, causing the cell to expand. And in this diagram over here, we see a red blood cell which is placed in distilled water, which is 100% H2O. And we see that the cell expands and expands as water moves into it in a hypotonic solution until eventually the cell bursts. It's called lysis, and it causes cell death. And the last kind of solution that is worth understanding is an isotonic solution. And this is a situation in which the water concentration is equal both inside and outside. And in this case, water will move in neither in nor out. Or another way to think about it is that it will move in and out equally. Okay? So there will be no net movement of water. No overall movement of water. And if there's no movement of water, this means no osmosis. Which is going to lead us to the next topic that we will have a mini lesson on, called active and passive transport, in which we'll look at the different ways that cells move molecules across a membrane.